Okay, I mean, we are going to have very short introductions as we mentioned, but it's a great pleasure for me to introduce today our speakers, David Huse from Princeton University. David works at the interface of ultracold atoms and condensed matter, mainly a condensed matter theories. He was reminding me that he was giving a lecture in the prior Boulder Summer School that we have on cold atoms, and he was telling me that at that time they discouraged him to talk about many body localization. And here we are today. He's telling us a lot of very interesting stories and physics about many body localization. So David, thank you so much for accepting to give the lecture today, and please go ahead.
Okay. Yeah. So please just yell out your questions when you want. That's what I like. Okay, so I'm going to give 3 lectures this week, and my topics are many-body quantum dynamics, thermalization. Most of today will be on these 2 topics, and many-body localization, which I'll mention a bit today, but that'll be more, we'll get into that much more, I guess, on Wednesday and Thursday. Okay. Right. So what I'm going to be talking about is a closed many-body system isolated from the environment. So no external environment. This is something that was an idealization when I was a student, but because of the developments in quantum information and in atomic AMO physics, this is now well approximated in the laboratory and studied quite seriously experimentally. And so it's become a very active topic of research, both theoretically and experimentally. Okay, so what I've drawn here, so this is my box, with impermeable walls, isolating it from the environment, right? And so now we have this closed system, which only contains n degrees of freedom with some finite n, although we'll want to take the limit of large n. N is large compared to 1, and sometimes we'll want to take the limit of n goes to infinity, but it's isolated from the rest of the universe. Inside the box, the degrees of freedom might be spins, they might be qubits, they might be optical lattice sites, which you could occupy or not with atoms or molecules. I like to say it that way because it's better to think about it second quantized when you're dealing with indistinguishable particles. So these are distinct, optical lattice sites are distinguishable degrees of freedom, and you can put indistinguishable atoms in them, but it's nicer to think about it that way. Okay, and then inside this box, these degrees of freedom interact with some Hamiltonian, which might have some time dependence if we have some classical external drive changing things. Sometimes this will be time independent, sometimes it'll be time dependent in my discussions. And that's what gives the dynamics. The dynamics is solely due to this Hamiltonian. I want to consider this generally, not make some weakly interacting approximation or something near 0 temperature. So we want the degrees of freedom to be strongly interacting. And we want the state of the system that if it went to thermal equilibrium, it would represent something with a non-zero entropy density, a non-zero temperature. So I don't want to use low temperature approximations. And occasionally I'll make weak interaction approximations, but we want to formulate things in a way that doesn't rely on that. Okay. And if you want to have a system coupled to an environment, just take a big part of the environment and put it in the box with your system and isolate that part of the environment from the rest of the environment, right? So within this framework here, we can think of a system coupled to an environment. We just make the environment finite and put it in the box also. Okay. And so a couple of the questions we'll be addressing One is, does such a system go to thermal equilibrium? Now, of course, in your statistical mechanics class, the teacher told you, yes, it does, right? And that's usually the case, but that's a non-trivial process. And sometimes it's not true. And it's very interesting to discuss how that works, when it happens, when it doesn't happen. Right? And so that's a big part of the interest here. And the question is, another way of putting this question is, if there's no external environment which brings it to equilibrium, can it do the job for itself? Can it be a bath for itself? Or can each small part of the system see the rest of the system as an environment, and that brings this to equilibrium? And if the answer to this question is yes, that's what we call thermalization. And if the answer to this question is no, which is the case for a number of interesting systems, one case where the system fails to be a bath for itself is, even though it's interacting and there's no obvious reason for it not to be a bath for itself, one case is many-body localization, which we abbreviate MBL, which is the strongly interacting high-temperature version of Anderson localization. Did it sound like someone was asking a question?
Yeah, I was going to ask a question on, we'll kind of push you to maybe elaborate a little bit or comment on aspects of this classical versus quantum. So, many of the things you can repeat for classical systems as well, but maybe there it's less of a question because,
These questions are very interesting classically, and I will address that. Mm-hmm.
Okay.
Some comments about classical. At the present point of our understanding, many-body localization as a robust phenomenon appears to require quantum and doesn't exist classically, although that's not certain. It may be that there is classic, so that's an interesting open research question. Is there structurally stable classical many-body localization?
Good, yeah, thank you.
Or we know you can do that, but is it fine-tuned, right? Is it stable? Quantum many-body localization is not fine-tuned. And I'll talk about those kinds of questions. I'll talk about the differences between classical and quantum thermalization. Yeah, absolutely. Okay, so that's a big part of all three lectures. And then for today in particular, if the answer is yes, which is what today's lecture is going to be about mostly, how does the apparent irreversibility of thermal equilibration, how does that emerge from the reversible dynamics from this Hamiltonian? Right? This Hamiltonian gives reversible dynamics. And so how does that all fit together? Which is an ancient question that Boltzmann worried about in the classical domain. And so I'll say some things about that. Okay, so before I erase any more questions, just yell them out. Okay, so we have this closed system undergoing dynamics due to a Hamiltonian. And the case, let me just mention there's some cases of this. So one is h of t equals h, time independent. And of course, if the system is truly isolated from the external world without even being driven, that is the case. In this case, because we have a time-independent Hamiltonian, we have a conserved extensive energy. Okay. Now, you know from your quantum mechanics course how to solve for the dynamics in this case, right? So what you do is you find the eigenstates and the eigenenergies. Okay, so these are now many body eigenstates. N, many body Hamiltonian. And then the dynamics is superficially simple, that the state, a general state of a quantum system is a mixed state given by a density matrix, and let's write the state of the system in the basis of the eigenstates of the Hamiltonian. And we can write the dynamics out exactly in a simple closed formula like this, sum over Nm, rho Nm. So here's the initial state. N. So if you know the initial state and you know the eigenstates and you know the eigenvalues, you know what the state is at all times. It's given by a one-line formula. Looks very simple, but that simplicity is completely deceptive because this is an enormously hard problem. And there's an enormous complexity in what are these eigenstates and what is this spectrum. So all the complexity is hidden, right? Here it's just a complete closed form solution. It looks very simple, but that's an illusion because the complexity is just being hidden. Of course, here I'm setting h bar equals 1. And now a special case is a pure state. A pure state is when the density matrix is just a projector onto a single state like that, and then the dynamics will be psi of t equals this is all standard, but it's good to just put it up explicitly. Zero. And there's the initial state goes in here, and then you just time evolve it with this unitary operator to get the state at later times. Okay. So that's one case. So this is a general mixed state. This is the dynamics of a pure state. Another case is we have so just write this way. More generally, to get the dynamics, we write I rho of t dt equals the commutator of h of t and rho of t. This is the general unitary time evolution of a state with a time-dependent Hamiltonian. And sometimes we actually consider just a general time-dependent Hamiltonian, and that's often of interest. Like this might be a random quantum circuit doing some operation, and then you might be able to actually solve this problem. And now there's another case, which we look at a lot, which is flow K. And so this is the case when our Hamiltonian is periodic with a period. So if the Hamiltonian is periodic in time with some period capital T, that's what we call flow K dynamics. Now let's just choose our time scale such that the period is 1. And then this Floquet system, Floquet dynamics, can be viewed as, actually, let me write it this way. It can be viewed stroboscopically in sync with the, turn off my chime. Right, so let me warn you, one thing that's going to happen. So this classroom likes to conserve energy, and the device that does that doesn't know I'm here. So at some point, the lights are going to go out. I'm going to go around, move around in the classroom and get them to turn back on. But it'll only be like 5 or 10 seconds. So I'm just warning you, that's going to happen. I don't know when. They've got it, you know, they assume there's fidgety students out in the audience, and they don't put it on the lecturer. So it doesn't work during pandemics very well. Okay, so this can be viewed stroboscopically, and what the dynamics is just this, that row at time 1 period later. So remember, I'm calling my period 1. Row at period 1 at time 1 period later is some unitary evolution operator that takes you through 1 period, like this. So this is the discrete time dynamics of a Floquet system. I'm going to erase and tell you what U is up here. Any questions about anything that's up here? I know it's pretty standard, but please ask. Okay.
Is that equation, so you have written more generally, and then there's an equation to the right of that. Is that the Schrodinger equation?
Yeah, this is the Schrodinger equation for a mixed state.
Huh.
This is equivalent to the Schrodinger equation. Yes.
You don't say. That's cool. Cool.
Yes. Some people
Well,
call it the von Neumann equation, because I think he was the first one to generally formulate it that way very soon after quantum mechanics. Yeah, really in the laboratory, the pure state is a fiction, right? If you're talking about many body physics,
Everything is a mixed
we
state.
never have the control to make a pure state. So the pure state is a fiction. We always have mixed states. And so quantum mechanics really should be taught right from the start in terms of mixed states. But unfortunately, that's not the way the textbooks are. They pretend that there's pure states all over the place, when it's just not true, right? As experimentalists know, right? You know, they can't, you know, making pure states is an enormous challenge. Whereas mixed states are, you know, that's generic quantum. Right?
Well, it's also nicely takes
So
out the
Schrodinger's equation should always be written this way. It should be never written in terms of pure states. But that's, you know, that's a difference.
It also nicely takes out the phase. There's no phase anymore, right?
Yeah, right. Schrodinger's equation's got this arbitrary phase in it, which is totally no physics, whereas this, it's gone. Yes, exactly. Okay, but anyways, so this unitary operator here that takes you forward 1 period in a Floquet system with a time periodic Hamiltonian. So this time periodic Hamiltonian, you know, for example, it could just be a radio frequency field you're applying to your system, right? And so it's subject to this oscillating field with a certain period, for example. Okay, so what is this U? This U is just the unitary operator that, so this U is now up here, and it's equal, so this now is the operator. This T is different from this T. So this T has been set equal to 1, and this is now the time ordering operator. And then you let that operate on e to the minus I integral from 0 to t dt h of t. So we just time evolve through 1 period. This is so that these Hamiltonians are all acting in order. And that defines the unitary operator that gives the time evolution from 1 time to a time that's a full period later. Now there is, in flow case systems, there is also, so this dynamics here tells you how to go from one time to one period later. Sometimes you're interested in not what happens one period later, but what happens during the period between this time and this time. So, and that's what is sometimes called micromotion. So the description I'm telling you here isn't the whole story of the dynamics, because you might want to ask, oh, what is the state of the system after a quarter of a period, right? And then you'd have to do there it goes. And then you'd have to make the operator that gets you only a quarter of a period through the dynamics. Okay. So, but I'm not really going to talk about that, because what I'm mostly going to be talking about is long times, not short times. So I want to ask, after many periods, does it go to thermal equilibrium, or is it localized? Okay. Now,
so David,
because, yeah, go ahead.
does this mean that if h of t is just a regular sine, then the integral is 0, so the unitary is just 1?
No, you don't just do this integral that way, because this time ordering operator, this expression is all full of commutators and.
Oh, so you actually have to expand it into a series and then do all of the multiplications in the
time ordering operator means that, you expand this out as a Taylor series, and it's got terms to arbitrary order in the Hamiltonian. The first term, yes, if this is sinusoidal, the sinusoidal term will integrate to 0, yes. But that's only the first term.
And so on, right?
All the higher order terms will be non-trivial.
Okay, thanks.
Assuming different parts of the Hamiltonian don't commute with each other, which of course is the case in the problems we're interested in. Yeah. Does that answer that question?
Yes, perfect. Thank you.
I'm sorry. Can you please remind me what we're trying to do here?
We're trying to get the dynamics. We're trying to understand, how does the state evolve as a function of time, right? So we have a Hamiltonian, which is periodic in time.
Mm-hmm.
It's making the dynamics by this equation.
Mm-hmm.
The state is changing. And if we go from one time to a time a full period later, the state will change this way. You take the state, multiply it by u on one side, u dagger on the other side, and that gives you the state one period later. That's the unitary time evolution, carrying you forward one period of the Floquet evolution.
Is this still for that isolated system you showed us earlier? The
isolated system that's what we have, all my lectures, okay? Now, why, you might ask, why does the Hamiltonian have a time dependence? Is that your question, maybe? And I meant to say something about that, right? If there's really no external environment, there shouldn't be any time dependence to the Hamiltonian, right? But I meant to say that if we have a time dependence to the Hamiltonian, it has to be due to a classical drive. So there's something external that's classical that the system cannot get entangled with, that's changing the Hamiltonian of the system in some pattern with no feedback from the system back to whatever that drive is, right? And that can be well approximated in the laboratory, where this h of t is driven by some coherent state of some, very high quantum number coherent state of some external system, which is therefore acting classically. Yeah, that's something I meant to say. I'm not sure if that was what you were asking.
That certainly helps. Thank you.
Yeah. Now, where was I? Yes. Okay. Now, because of this evolution, the dynamic, right, with a time-independent Hamiltonian, you have a certain translational invariance in time, which is the symmetry that says you have conserved energy, and it says you have eigenstates, right? With the Floquet system, you only have discrete translational symmetry in time. Translation, quote, you know, under time changes, you have this discrete symmetry. If I move it forward a whole period, I'm back to the same situation in terms of what the drive is, right? Or what the Hamiltonian is. And so we have eigenstates of U. So Floquet systems like time-independent Hamiltonians have eigenstates of the dynamics. And let me just, so. And because it's an eigenstate of a unitary operator, the eigenvalue has to be a unit magnitude complex number. So I just write it as a phase, phi. And these eigenstates, if the system is in an eigenstate at time t, it will be in that same state any integer number of periods later. So it's stroboscopically time independent. Of course, during the period, it's doing some microemulsion, but after every period, it comes back to the same state up to this one phase. Right? So like time-independent Hamiltonians, Floquet systems also have eigenstates, but they don't, the eigenvalue is not an extensive conserved energy, it's just a phase. Right? So you don't have the extensive conserved energy anymore. And then the general dynamics, which I wrote down before for the Floquet system, it looks like this: rho of t is equal to some alpha beta, rho alpha beta of 0. There's the initial state, and then alpha e to the I. This is, sorry, rho of n after n periods. Time equals n periods after the initial state, phi beta times n times beta. So that's the dynamics of a Floquet system. The initial state is here. The eigenstate, in terms of the eigenstates, right? We find the eigenstates of U. U on this side, it's the alpha, gives e to the I phi alpha, one factor of that for every period you move forward. And U dagger on this side hits the beta, gives an e to the minus I phi beta, one factor for every period you move forward. So this is the analogous formula for Floquet systems. Again, looks very simple, but the complexity is hidden. What is the nature of all these eigenstates? What's the nature of this spectrum? That's quite complicated. And so all the complexity is hidden in solving this equation here. Or a lot of the complexity.
Oh, just to clarify, is phi complex? No, it's real.
No, phi, this is just a phase. It's real between minus pi and pi, say. Let's choose it to be between minus pi and pi. Right? Okay. So this is a unitary operator. Mm-hmm. So its eigenvalue, its spectrum is on the unit circle. Mm. And so every eigenvalue of U, I can just write as e to the I times a phase, and I can choose the phase, say, to be between minus pi and pi.
Okay, thank you.
Including one of those as an option.
Okay, thanks.
Yeah. It's really the analog of e to the I e alpha t, right? If it were actually, a special case of a Floquet system is nothing's changing during the period, right? That's a special case of the Floquet system, right? And then this would be, or there'd be a minus sign, so it would be e to the minus I e alpha times the period, right? That's what it would be if it was a time-independent Hamiltonian, right? And this phi alpha corresponds to the minus e alpha times the period.
Yeah.
But more generally, it's just a phase between minus pi and pi, and it doesn't necessarily correspond to an energy.
Cool, thanks.
Certainly not an extensive energy, right? So sometimes people say, oh, it's an energy modulo 2 pi over the period, but I don't know that that's very helpful. I think it's better to just think of it as a phase. Okay, so that's what it is in the case of a time-independent Hamiltonian. Okay, I'm going to erase this. Any questions about what's down here? Okay, so just to summarize that there, closed system dynamics, what I just told you. Okay, so we're going to have, so this is now closed system dynamics. And I'm going to lay this out. So in this direction, we get more symmetries. Okay. And so we can have a general unitary with an h of t with no periodicity, time dependence, no symmetries. So this is the case, no symmetries other than just the unitarity, the closed system. You can view unitarity, which is the norm of your state is preserved by the dynamics as a symmetry, right? But that's the only symmetry, a unitary system with a Hamiltonian which has no periodicity. That's the only symmetry it has. Okay, and then we can make h of t periodic.
So would you,
That gives us a Floquet system. So this is a symmetry under translating in time by one period. That makes a Floquet system. And this now has eigenstates. This really doesn't have time-independent eigenstates because the Hamiltonian keeps changing. So this is more symmetry, right? And now we can make h of t equals h, make it independent of time. And that's what I would call, so often when we're talking about Floquet systems, we say a Floquet system or a Hamiltonian system. And by the Hamiltonian, we mean time-independent Hamiltonian to distinguish it from the Floquet, which has a periodic Hamiltonian, which is changing with time, right? And this is an extra symmetry, so it's changing the symmetry under time from discrete to continuous. And this gives, as I said earlier, an extensive conserved energy. And then each of these we could have, so we could have a general aperiodic Hamiltonian that conserves something else, like particle number or spin or something. So we could have unitary with more symmetries. You can have conserved particle number, magnetization, you might have some integrabilities, you can add a lot more symmetries other than these symmetries I'm talking about here. And so people study models that have unitarity and some other symmetry that's not one of these, right? And with a Floquet system, you could do Floquet with more symmetries. And similarly with Hamiltonian. So when one talks about, you have a dynamics, and then you have the symmetries. What are the conservation laws? Are there eigenstates or are there not? what are the conserved quantities? And so this is sort of a general landscape. Just because people are used to it, I will mostly talk in the Hamiltonian, time-independent Hamiltonian language, because that's what people are most used to, except when it's better, except when I specifically want to say something about one of the other cases. But in fact, if you want to study many-body quantum dynamics, just the dynamics, and not all the detailed physics associated with symmetries, you should study this, because it has all the essence of many-body quantum dynamics without the distractions of these other ingredients. And so, although we naturally tend to work here or even over here, a Hamiltonian, say with a conserved particle number or something, a lot of times it's simpler to go back and take away all the symmetries that are not essential to the physics you're interested in. And that often makes a simpler way of understanding what you're doing, right? And so that's something that's happened a lot recently. People have, we studied MBL here, and then we realized, no, the conserved extensive energy, this is not important to MBL. It's much better to study flow K models, because you're not distracted with this other physics, which is not really an essential part of MBL, for example.
David?
Yep.
Can you comment on, so in equilibrium systems, we talk about, systems with symmetry can be broken spontaneously. Can you say something about that in this context, non-equilibrium context? So is that can also happen, or?
Oh, absolutely, absolutely. I don't know that I have much to add about that.
You're talking about dynamical phase transitions like time average quantities, or what you?
Yeah. No, there's like you could say, what if, what's happening with the eigenstates and the spectrum in a dynamical Ising model when you go into the ordered phase.
That's right. That's right.
And yeah, there's interesting stuff there. I wasn't planning to cover it, but there is interesting stuff there, having to do with how the broken symmetry shows up in the spectrum and in the eigenstates. But that's really not on my agenda.
That's fine. That's fine. I just wanted to.
The thing is, the other thing we've realized in this is, I'm a condensed matter physicist, and condensed matter traditionally has been about low temperatures where, that's where all the interesting stuff happens. The symmetries break and everything interesting is at low temperatures, right? And well, even with cold atoms, people say, they're ultra cold, right? But they're only ultra cold on the Kelvin scale, right? On the scale of their own interactions, they're actually very hot, right? Compared to condensed matter systems. Condensed matter systems are much colder than ultra cold atom systems on their own energy scale of their own interactions, right? So ultra cold atom systems are actually very high temperature physics on their own terms, right? Because the ability to cool them is just primitive compared to what we have for condensed matter systems. Sorry to say that to the experiment, it's true. But we've realized is there's very interesting dynamics happening at high temperatures, even at infinite temperature. Probably Wasim Bakr will give you a lecture about some interesting dynamics we found in his system at infinite temperature. So he has an optical lattice and he tilts it, and it's only one band, and in that one band, the system goes to infinite temperature. It has subdiffusive transport. So there's very interesting stuff happening in quantum mechanics at very high temperatures. And so that's why, in some sense, Leo, the symmetry breaking, that's old-fashioned stuff.
Okay.
Right. And so we're sort of now, saying, there's this whole world at high temperatures that's super interesting. And so let's leave that stuff aside. right? Of course, we can merge the two things back together, but I don't really have time to do that.
Okay, fair enough.
Yeah.
Can I ask a question?
Yeah, go ahead.
I'd be really interested in better understanding how to maybe design a Hamiltonian, a Floquet Hamiltonian that behaves or that obeys certain symmetries. How to choose a Hamiltonian that has a symmetry that I want.
Well, the simplest thing is that the simplest way to do it is, it has a periodic Hamiltonian, right? And if you want a certain symmetry, the simplest thing is to say, I want my Hamiltonian to have that symmetry at all times, right? I could give it a periodic structure in time, but keep the symmetry at all times, right? And if it has that symmetry at all times, the Floquet operator will have that symmetry. So that's in some sense the simplest way to do it. Of course, you could fine tune it so that it broke the symmetry at one time, it broke it another way at another time, but then the Floquet operator ends up having the symmetry. But that's usually not the situation. That would have to be very fine-tuned. So having symmetries in the Floquet system, it's not something subtle. What you just do is you just have the Hamiltonian have that symmetry at all times.
Okay.
Yeah, no, that's a good question. Okay, so let me erase and continue. Okay, now maybe just say some, okay. So the limit n goes to infinity is, as you've learned in your statistical mechanics class, it's conceptually useful. And concepts like that I'm going to talk about, thermalization, just thermodynamics itself, phase transitions, which Leo was just mentioning. These things only become sharply defined in this limit of an infinite system. Now, I might say the thermodynamic limit. I'm trying to break myself of that habit because often we're not doing thermodynamics. And so I like to say the large system limit or the n goes to infinity limit. But if I say the thermodynamic limit, that's what I mean. But we're interested in questions in that limit that aren't thermodynamics, right? And so that's why I don't want to use that term. Now, of course, a system in the laboratory is never in this limit, but this limit is a very useful reference point. The system in the laboratory likely or can have a large enough number of degrees of freedom so that this limit is a very good reference point to compare it to, much better than a very small system, right? And for some systems, you get into that regime for surprisingly small systems. That you only need like 10 degrees of freedom and it's behaving much more like the n goes to infinity limit than it's behaving like a system of 2 or 3 degrees of freedom. And that's actually lucky for us because it means, when we do, these quantum problems I was telling you about, you've got to get the eigenstates, the eigenenergies. Basically, if you're doing a strongly interacting problem, a lot of what we do is we study hard models and we just have the computer solve. And the system is very small, very small. But fortunately, on the sizes we can diagonalize on the computer, a lot of the physics of the large n limit does come out, right? And that's what has allowed this field to really develop, right? If it had turned out that you had to get to 100 degrees of freedom before you started seeing this behavior, we would have been screwed, right? Because we can, on a lot of the models we're talking about, we can only get up to like 20 degrees of freedom before the computers run out of steam, right? And so if that was all very small systems, we just wouldn't be able to explore the large system limit. But fortunately, the boundary is not at 100, the boundary is at 6 or something, in a lot of models. So you really can get into this regime. Okay, so I'm going to talk a lot about this limit, and that's just sort of just saying some things about it. It doesn't really exist in the laboratory, but it's conceptually extremely useful.
I have a
approximated reasonably well in the laboratory.
I have a question. Is there any intuition of why is that the case? That I mean, you don't need 100 degrees of freedom to actually see that.
We do have problems where you do need much. It's basically if your system is very strongly interacting and you're not at low temperatures, there's no small parameter in the problem, then there's no reason for that number to be big compared to 1. Of course, you can make it large. Like in many body localization, we now think to really see the phase transition, you do need 100 or so. And we're not really seeing it. We're seeing something else in our numerics, right? And so it depends on the problem. But, oh, there it goes again. But essentially, yeah, if your problem is, has no small parameters in it, there's no reason for that crossover number to be big, right? And that is the case for a number of models. And that allows this physics to be explored numerically with modest computer resources, and you can really learn something and get some confidence in, so, right, a lot of the theory we do, it's uncontrolled theory, right? It's sort of assumptions, hypotheses, and you only test them numerically or in the laboratory. Right? So that has been very helpful. Okay. Right. So now I want to say something. Okay. So we're talking about quantum mechanics, and so let me just say something you learned in your quantum mechanics course. So all observables are permission operators. And that's fine. Now, whoever taught you quantum mechanics might have said the opposite. All Hermitian operators are observables. That is false, right? And I want to say what I mean by that. So in the n goes to infinity limit, almost all, in the mathematical sense, Hermitian operators are not observable. And I want to explain to you why I'm saying this. And of course, to an experimentalist, that's obvious, right? The experimentalist knows that you can't make a measurement which involves an infinite number of degrees of freedom. You might be able to measure something involving 12 spins, or maybe 20 spins, and maybe 2 decades from now, 80 spins or 100 spins, but not infinity, right? And so what do I mean by an observable? I actually literally mean something that you could observe in the laboratory, right? And I think, and for that to be true, it has to be an operator which is of a finite order in the degrees of freedom that you can couple to. It can't have this divergence in it. Okay. So as an example, let's say we have n spin 1/2 or qubits, right? Okay, so we have a system. It consists of qubits or spin 1/2, and there's n of them. We have 4 to the n operators. There are 2 to the n states in your Hilbert space. There are 4 to the n operators, which is the square of that. And so each spin has 4 Pauli operators, which I'll call 1, x, y, and z. These are the Pauli operators. This one's the identity. So, and a single spin operator, there are only 4 of them. Every single spin operator is a linear combination of these 4 operators. And so a basis for the 4 to the n operators, which are linearly independent and in a certain sense orthogonal, is just take a product of one of the 4 Pauli operators on each spin and multiply them. And that's why there's 4 to the n of them. So there are 4 to the n Hermitian operators. You can make them all Hermitian by putting your eyes in the right place. So these are outer products. Single spin operators. But now when we take the n goes to infinity limit, almost all of these operators are a product of an infinite number of non-identity spin operators. And that's something that is not observable and really never will be observable. The experimentalists will get to the ability to measure a certain number of spins, but that number will always be finite. I think we can be pretty certain of that.
I have a question for that.
Yeah.
But there are also like non-local orders where maybe there's some ETH states and there's bulk edge correspondence. Like the ETH states, you can measure them and they can tell you about the bulk. Then can you say that the bulk operator is observable through those ETH states? Something of that sort?
Well, that, you know, I said almost all. So that might give you 2 more operators that become observable, right? Or some finite number of additional operators that become observable. But you're not going to get an exponentially large number of operators that you can observe that way, right?
Well, also, I mean, could you say that the physical operators, the observable ones, are the local ones?
Well,
No.
Meaning there's
you know, in neutron scattering, you measure correlations over large distances or X-ray scattering.
I see.
Right, and
Yeah.
so a 2-point operator at a very large distance, you could call it non-local, but it's observable,
Yeah.
right? So it's not the locality in terms of the distance between the.
It's in the
degrees
Fox
of freedom.
space. Yeah.
It's the number of degrees of freedom. The
Also, we
difficulty
can-
is the product of operators.
Yeah.
When you take a product of an enormous number of operators, that's what becomes difficult to measure.
Yeah.
To just say, except to some special situations, for example, in the ions, we can measure a fidelity that involves n ions operator, or we can only measure the probability to be dark, because if there is a single count flip, then we cannot distinguish, but we can distinguish the probability to be all dark. So, for example, there are capabilities to measure parity operators or fidelity operators, but in very limited situations.
Right, and in that situation, it's just going to be of order 1 such operators, right? You're not going to
Yes.
get exponentially many such operators that you can measure that.
Exactly.
Yeah. So when I say almost all, right, of course, the number of operators that are observable is also infinite when you take n to infinity. So I'm not saying there aren't any observables. There are infinitely many observables, but the number of non-observables is a much bigger infinity. And that's what the almost all means. Almost all of the operators are non-observable, even though there's an infinite number that are observable in this limit. Right? So if we just add a few more examples, it doesn't change the statement. Right? You just have this enormous operator space that you have. Okay. So let me just give an example of an observable and just emphasize one point. So for example, we could do the following. If we have n spins, we could take the x Pauli operator on spin 22 and the outer product of that of the y operator on spin 773 times the z operator on spin 614. And then it's important to say times the identity operator on all other spins. Right? When we say an operator and we only mention a couple of sites, we always mean it's times the identity on all the other degrees of freedom, right? And that's the key, is as n goes to infinity, if you want it to be observable, it has to be the identity on almost all the spins and non-identity on just a small number. And then it could be observable. And that just makes it a much smaller number than 4 to the n. Right? Now, why am I belaboring this? And I'll give you one reason why. And I'm giving local operators a special status. I have some degrees of freedom, and I take my operator and I ask, it's a product of how many local operators, right? I measure how difficult the operator is by the product of how many, right? Adding them up is not a problem, right? In X-ray scattering on a big sample, you add up 2-point functions over all pairs of sites, right? That's not a problem. It's the product of operators that's difficult. Okay, but we're giving these local operators a special status. So when we say a system is a many-body system, it consists of bodies, right? And there are many of them, right? And the Hilbert space of the full system is an outer product of, or maybe a subset of the outer product of the Hilbert spaces of all these local degrees of freedom, right? And it has that structure. That's an important part of the physics. You shouldn't just consider an abstract Hilbert space with no structure to model a many-body system, right? A many-body system has a Hilbert space that naturally factorizes in terms of the degrees of freedom, right? So a random matrix is not a good approximation to a many-body system. It doesn't have the structure of a many-body system since its Hilbert space doesn't have this factorization structure. Okay, but let me say something here. So why I give local operators a special status? Right, and many people discuss many-body problems without worrying about this. So let's consider a Hamiltonian. So consider a Hamiltonian, and I'm just going to write it in terms of its eigenstates. So H is equal to sum over its eigenstates and E sub n. Or if I have a flow K, U is equal to sum over alpha u to the I phi alpha alpha. Now, if we didn't give the local operator special status, this has many conserved operators that commute with the Hamiltonian, namely all the projectors onto the eigenstates, right? All the projectors onto the eigenstates commute with this Hamiltonian. Put a different letter here, K. Right? They all commute with this Hamiltonian. So if we didn't give local operators a special status and allowed all Hermitian operators to be on the same footing, every Hamiltonian is integrable with an infinite number of conservation laws. It never goes to thermal equilibrium. So you just get sort of silly results. And there was a nice paper by this guy, just write his name out, spelled properly, which was published in 2013, that really made this point in a nice way. And that's where I really began to fully appreciate it. So if we want to make meaningful distinctions between systems that are quantum chaotic or not, or do thermalize or not, we have to make distinctions amongst the Hermitian operators as to which ones are observables and which ones are not.
So here, are we also considering the Hamiltonian to be composed of local operators, or not necessarily?
This is true for any Hamiltonian, whether it's many body or not. You could write it this way, right? And if we gave all operators in this Hilbert space the same status, this Hamiltonian or any Hamiltonian is completely integrable with this infinite, this set, one conserved operator for every state in the Hilbert space, right? And if I started off, with some particular linear combination of these operators, the probability in that state in the closed system will never change. So it'll never go to thermal equilibrium. You can't even really define what thermal equilibrium would mean in the closed system in that case. You'll see how I'm going to define thermal equilibrium. My definitions don't even work if I don't give certain operators a special status and let most operators be non-observable. But you'll see that as I go along.
Okay. Thank you.
Dave, but just to make your point, to finish your point, those operators that commute for generic Hamiltonian, this extensive number of operators, most of them are unobservable. That's why it's non-integrable Hamiltonian.
I should have said that, yeah. For most Hamiltonians of interest, these eigenstates are very complicated, and this operator you make by projecting on it is not an observable.
Not an observable.
Some totally complicated, completely non-local operator that's a product of many local, of n local operators, and so it's not an observable. So these projections onto eigenstates for most Hamiltonians are not observable operators. Yes, thank you, Leo. I should have said that.
Did you explain what you mean by give a special status? It's not super clear to me. Do you mean like that they're not part of the Hamiltonian, or is there any way of enforcing that they're not observable?
The special status is certain operators are observable, and in the limit n goes to infinity, almost all of them are not observable, right? And so I've given some small subset of all the operators a special status of being observables.
That sounds like a practical consideration rather than like a restriction on the dynamics, and it seems strange.
No, it's not a restriction on the dynamics. It's a status which, when I define things, which I'm going to do, like I'm going to define what do I mean by thermal equilibrium. And in order to define that, that's one of Liszkowski's point. In order to even define that, you need to give a subset of the operators a special status. Otherwise, you just can't even define what you mean by thermal equilibrium. So
okay, I'll wait
you know,
for
the utility of this, I hope, will become a little bit clearer.
So you say like we're giving local operators a special status, but are we still saying like just operators that consist of like a small number of like non-identities, or like they don't have to be physically local, do they?
Right. No, we have the local operators, and then the observables are operators that are products of a finite number of those local operators. They don't have to be near each other, right? I could have the product of this spin here and this spin very far away. That's a 2-point operator, could be at very large distance. That's an observable, right? You know, people do teleportation experiments where, you know, they've got a qubit in one lab and another one kilometers away, and they're observing those operators, right? So those are observables, right? They only involve a small number of qubits.
And like a unrelated question. So you wrote this down for like Hamiltonian dynamics and also for like flow K system off to the side. Like, does this also, can we also make these distinctions for just like the general, like the most general case of just unitary?
Yeah, but I couldn't make the point I made here that if I don't give them special status, everything is integrable, right? But if I had a time into a Hamiltonian which wasn't periodic, I wouldn't be able to say I have a whole bunch of conserved operators, right? So that's, I wanted to make this one particular point that, which is only specific when you have eigenstates.
Okay, thanks.
Yeah.
Do you only mean local in? Oh, sorry.
No, go ahead.
Do you only mean local in position space, or do you include local in, say, momentum space, which would be delocalized?
Yeah. So since sums of operator, you know, sums of observables are observables. So, you know, say a number operator in momentum space is the sum of a bunch of number operators in real space, or products of creation and momentum's, you know, going from momentum space to real space is just doing sums, not products. And so observables in real space can be turned into observables in momentum space just by adding them up with the right phase factors, right? So my operators that I'm talking about could be in momentum space, yes. Absolutely.
So for
when I say, right, so this word local, right, there's local in physics, and then there's local in computer science, which is, you know, what is a basic degree of freedom, right? And I'm more using local right now in the computer science sense, right? Not, it doesn't mean short distances. It just means a basic degree of freedom. Right? So local isn't necessarily the best word for it, right? We have a many-body system. Its Hilbert space is an outer product of Hilbert spaces of the individual degrees of freedom. And those individual degrees of freedom I'm calling local, right? Now you could have done it all in momentum space, and then local would mean local in momentum space.
Yeah. So for the definition for integrability, are we thinking about like having a infinite number of conserved quantity, or a lot of conserved quantities, or we are more thinking of like the GOE Poissonian thing?
Yeah, integrability. By integrability, I mean a system with, you know, a divergent, in the n goes to infinity limit, it has a divergent number of conserved operators that commute with the number.
Okay, thank you.
And these are special cases. Well, a divergent number of observable operators that commute with the Hamiltonian, and those are the integrable systems, right? Of course, if we allow all operators, every Hamiltonian has a divergent number of conserved operators, right? But we shouldn't consider these in that discussion because these are just not observable.
Yes, that makes sense. Thank you.
Yeah. Okay, so how am I doing? I got 15 minutes. Okay. So what is thermal equilibrium of a closed system. That's our next topic. Now, to make this a sharp question with a sharp answer, we need to take the limit of infinite number of degrees of freedom. Otherwise, it's not sharply defined. Okay. Now, if we have extensive conserved quantities like energy or particle number or magnetization, we need to specify the density of those. So for example, this could be energy. So we could specify the energy density to specify what thermal equilibrium we're talking about, or the conjugate variable, the temperature. We could have the particle number, particle density, number density, or the conjugate variable, the chemical potential, etc. Okay, so thermal equilibrium has parameters. For every conserved quantity, you have to say, you know, which point, which equilibrium are we talking about? What energy density or what temperature, what particle number density or what chemical potential? You could pick this or this depending upon how you want to specify it. And of course, if we have no conservation laws, if we have a flow case system with no conservation laws, you don't have to specify any of these things. There's only one thermal equilibrium because there's no conservation laws. And that's one of the nice things about flow case systems is they make thermal equilibrium very simple. Okay. And then at thermal equilibrium, the entropy is maximized given, whoops, here we go. Given the various parameters. So say you fix the temperature, fix the chemical potential, whatever else. At equilibrium, equilibrium is the maximum entropy given those conditions. And so what we do, so we average over all states with those conditions. And this defines an ensemble. You know, there's various ways of doing it. You can, constrain these to fixed values and make a microcanonical ensemble, or you can constrain these, make canonical, grand canonical, etc. And this produces an ensemble with the maximum entropy given the constraints. Now, right, and we have to, right, so this is actually an important point, specify the density. You can take the limit n goes to infinity such that the system doesn't even have a thermal equilibrium by picking peculiar states where they don't have a density. There's some sort of Schrödinger cat state where they're a linear combination of something at low temperatures and something at high temperatures. And so they don't even have a temperature, right? And then they don't really have a proper thermal equilibrium. But those states are enormously hard to prepare. Almost all ways of preparing initial states in the laboratory, you end up with a density with a quite narrow probability distribution. And then, so we do need to restrict ourselves to states that in the limit n goes to infinity, these densities go to a particular value. The temperature goes to a particular value, and it's not something where it's Schrödinger cat light, where you have two different equilibriums, both in the same system, or even more than two.
So David, how do you talk about temperature and chemical potential if you're speaking purely about closed system? So there's no concept
As we do in thermodynamics.
Well, we usually
As we do in statistical mechanics, right? Right. If I have a system with a given energy density, and I know how to do the statistical mechanics, I can figure out what that temperature is.
Sure. Okay. But you don't mean.
So
but it's
right
really
now,
the first. It's really the first set that's well defined. It's not, and it's the second set that is derived.
Well, when I do the average over all states with these conditions and make an ensemble, right? I could say, I'm going to say, my energy has to be between this and this, and I could make the microcanonical ensemble, right? Or I could do this with a Lagrange multiplier in order to constrain the energy to be where it should be, and that would make the canonical ensemble.
But I guess what I mean is physically.
And those have the same entropy density, right? And we know from statistical mechanics, these are both perfectly fine things to do, right?
If your system equilibrates.
Well, no, right now I'm just saying for a given energy density, what is a thermal state, right? I'm not saying the system does go to the thermal state.
Oh, okay.
I'm just saying, how am I going to define it?
Okay.
Right? Mm-hmm. So if it went to the thermal state, what would that look like?
Mm-hmm. Okay.
Right. So now we're like back in statistical mechanics where we just assume it thermalizes, and then we just talk about how that works. The question of whether it actually goes there, we're leaving aside. We first need to define what that question means before we try to answer it, right? And so I need to define what thermal equilibrium is. And the definition of thermal equilibrium, as you'll see, is much bigger than what you learned. There are, thermal equilibrium is a much more flexible concept than you learn about in the statistical mechanics textbooks.
David, I have a question related. For example, imagine that the magnetization is conserved. You have an exchange model, sigma plus, sigma minus. So total SC, the magnetization is conserved. Right. But it's not only total SC squared, SC cube. So do you need to include all the type of in principle, there is going to be a Lagrange multiplier associated with SC, but there is going to be an Lagrange multiplier associated with SC squared and so forth. So
if you prepare an initial state in the large N limit with a definite magnetization density, of course it will have some probability distribution. Mm-hmm. But unless you're able to, in a typical experiment, that's going to look like a Gaussian, right? You're not going to have the control to shape that distribution so you care about what all the moments are doing. Now, maybe you can in some special experiment, and then you would have to worry about it. Absolutely. But let's say for now, we're not going to worry about being able to do that. Yeah, so I know you probably know how to do that.
It's very subtle.
And then you would just have to add it to the list of conserved quantities, right? And but let's say for now, your control of initial state preparation is such that you just control these densities, and the probability distributions are going to be Gaussians, and the central limit theorem will apply as you take the limit of n goes to infinity. And so we don't have to worry much about, and the width of the Gaussian gets narrow. So really all we care about is the first moment.
Okay.
If you end up caring about the higher moments, then that's actually more conserved quantities you have to pay attention to, I think. But let's leave that aside.
Okay.
Yeah. Okay. So this gives an ensemble, and the ensemble gives probability distributions for all observables. Right, and in the limit n goes to infinity, as you learned in your statistical mechanics course, these probability distribution, what is an observable? An observable is a small subsystem of the big system, right? It involves just some finite number of degrees of freedom, right? So you learn in your statistical mechanics course that you can take all these different ensembles, each of which has its own advantages and disadvantages, but in the limit of n goes to infinity, the probability distributions of the observables are the same in all those equivalent ensembles. And those ensembles are all thermal equilibrium, right? So we already know there are multiple different thermal equilibriums for a closed system. And so what do we mean by thermal equilibrium? Thermal equilibrium is a thermal state. So when I say a thermal state, I mean one that is at thermal equilibrium. And it's really only sharply defined in the limit n goes to infinity. And it's any state. And it could be pure or it could be mixed with the same, in this limit, probability distributions of all the observables. And the number of thermal states for a given system is just absolutely enormous, and you just learned in statistical mechanics about a couple of them: the microcanonical ensemble, the canonical ensemble, the grand canonical ensemble. But there are, enormous numbers of them, right? And so when a system goes to thermal equilibrium, you don't know what state it's in. You only know it's in a state where the observables have the equilibrium probability distribution. You know that. But that's not very much information compared to all the information in the state. It's just the observable information, which is a very tiny fraction of, right? All the non-observables, they could be doing whatever they want. And you would never know it because you can't observe them, right? And so there's this enormous freedom in thermal equilibrium that allows, and that's what allows you to start from some crazy non-equilibrium state, have it undergo a deterministic unitary evolution, and it goes to thermal equilibrium, no matter which state you started with, if it's a system that thermalizes. And it's because there's an enormous freedom in what the thermal states are. And why is that? The thermal states are the states of maximum entropy. There's an enormous number of them. In fact, almost all states under those conditions are thermal equilibrium. The non-equilibrium states are the special states. Thermal equilibrium is just the generic behavior, right? And this is something von Neumann showed right at the beginning of quantum mechanics. If you just draw a random state out of a Hilbert space, it's at thermal equilibrium under something, this is what they call typicality. Okay, so that's defining what I mean by thermal equilibrium. Should I, well, I don't know. My time isn't up. We've had a number of questions. What's the routine here? Do I actually stop at?
Well, I mean, how much time do you need? Do you need extra time, extra 5 minutes, or how much time you need to finish?
I'll take an infinite amount of time if you'll give it to me.
But more seriously, like if you can find.
I just want to follow your conventions. Should I stop right at?
No. I mean, the answer depends on how much time, whether it makes sense to finish something up in the next few minutes, 5 minutes, let's say.
Okay. Well, let me just maybe not finish up something, but say what we're going to do next.
Okay, that's great.
I'm taking my time and I'm not going to get through my lectures, but I think that's good. I like that when I get questions and we go over things carefully. I hope that's what you guys like.
That's what we want.
That's the idea.
Okay, so the next thing is thermalization is a dynamical process or question. We start in an initial state that's out of equilibrium. Okay. Let me just say a couple more things. Okay. First of all, it's not proven for really any realistic system. But it's well documented, it's pretty well understood theoretically and pretty well demonstrated for many systems numerically. Okay. But it's too hard to just do it analytically and prove it. Okay. So we start out of thermal equilibrium. And what does that mean? It means some observables, let's call them A for some operators, which are observables, have probability distributions different from thermal equilibrium. TE is thermal equilibrium, right? That's what we mean by being out of equilibrium. So for example, if it's an optical lattice, some states have a higher occupation, some have a lower occupation. That's something they often produce is a staggered density, right? You interfere some light to put more atoms on the even sublattice and less atoms on the odd sublattice, and then you take away whatever drove that and ask, does it equilibrate? Right? That's a sort of a simple out of equilibrium situation that's often prepared. Right. And then the question is, what happens to this, right? We have these observables, they are out of equilibrium. The dynamics is deterministic and reversible. So the fact that these were out of equilibrium, that information is still in the system at all times. So how did the system go to thermal equilibrium? And that's what I want to talk about next, as a dynamic process, how that works. But I think given the time, why don't we, so that's just sort of a teaser for next lecture. And I have to maybe tune my priorities to see what happens with the next two lectures. But I like to go over this thermalization very carefully and thoroughly because this is what most systems do, right? I could spend a lot of time on many-body localization, which is sort of more exotic, but most systems do this, and this is very fundamental and is worth really understanding, really deeply, right? And so I think I will keep this focus, and I hope that's okay.
Sounds great.
People can send me their opinions if they think I should move the focus more towards many-body localization rather than thermalization. But, okay, so I'm open. So that's all I'm going to say today. But let's have many more questions if people are still awake and want to ask.
I mean, there were plenty of questions during the lecture, so I don't know how many there are now.
David, will you define what you just said more precisely? Information and those out of equilibrium local operators?
I'll try to, yes.
Okay. Because it's often,
on Wednesday.
Okay, good. it's often stated as a nice picture, phenomenological, as a nice picture, like there's an information but I haven't seen it defined carefully, but.
Yeah.
Okay, good.
Yeah, I'll try to do that, and you challenge me if I don't succeed.
Okay, sure. I will.
And Ehud will have another chance next week.
Yeah.
So, I know the fancy stuff. If I don't get to it, Ehud will get to it because he moves along a lot faster than I do.
Excellent. So if there are no more questions, maybe the students get a break until 4 p.m. where we have our last lecture of the day.
Sounds good. Thank you, David.
Thank you, David. It was very nice.